Alright, so let's get back to the lecture. This is lecture number 3, part 2. In the first part, we looked at the concepts of permeability and porosity and how to calculate them. The next part here, first we'll look at the concept of lithification, and then look at the relationship between lithification, textural properties, and also porosity and permeability. Okay, so we'll go to lithification first. This is the process of transforming sediment into sedimentary rock. You've already gone through the topic of lithification and diagenesis in first year. I'll just give you a brief summary here. Okay, so lithification is the process of hardening a loose sediment into sedimentary rock. Okay, and we do this through two main processes. One is through compaction, second is cementation. So compaction is the process resulting in collapse of pore space in a sediment. You can look at this diagram here. You start with the initial deposit, let's say on the seafloor. You have a sand being deposited, so you have your primary porosity and your primary grains here. But when you start to lay down more and more sediment on top of it, there's a lot of burden now on the original layer, the older layer, right? So your grains are arranged to become more closer and closer together, right? You're losing space. So this is compaction, all right? Become more and more compact, more and more compact in this case. So then you have the second process, which is cementation. So this is where you have, you get minerals precipitated out from solution. So you have water inside your pores, and the water can flow through the pores if you have permeability, right? And the flowing water also brings with it these soluble ions. Given the right conditions, given the right temperature, given the right pressure, given the right chemical composition, you start to get crystals growing out. Maybe calcite crystals or aragonite or any kind of mineral, and they start to fill in the pores to form a cement. So this is growth or precipitation of minerals in pore spaces. It's called cementation. So lithification in general is a process of porosity destruction through compaction and cementation. Generally, you lose porosity because of compaction and cementation. But I'll show you later that is not always the case. Yeah? So here we are going into more detail. Compaction involves mechanical dewatering, meaning that when you compact a sediment, you have less and less space, right, in between the grains. The water inside the pores will be pushed out. So that is dewatering. Okay. And that happens because, progressive loading of sediment under several kilometers of sediment. Sediment under pressure tends to undergo compaction, pore water is squeezed out, and grains are rearranged, and they can be amalgamated together. There are two types of compaction. First is mechanical compaction, and second is chemical compaction. Let's have a look at these two types. So mechanical compaction is easy to understand, right? So you have loose sediment, when you put more and more burden on top of it, so you're losing space, it becomes compacted. Jadi mampat. It's physically compacted, right? So what happens during mechanical compaction is that the grains are rearranged, so you get different packing configurations. We've learned about packing before in textures, right? In grain fabrics. First, you just get rearranging of the grains. So maybe you start with this kind of cubic packing here, and then because of more loading, it becomes rhombohedral packing, losing space. Now, after some time, you cannot lose any space anymore as you compact. So what happens next is your grains start to deform. If your grains are ductile, it can undergo plastic deformation. So for example, here, this is a mica grain in between other kinds of grains here. So your mica grain bends. This is ductile deformation because of the compaction. Okay? being pushed together by these two grains here. So this is bent. Okay, so that is ductile deformation. But you can also get brittle fracturing, brittle grains. Okay? You get fracturing here and here because these are more brittle grains. Okay. Sorry, this is a ductile grain. You have deformation along the contacts here. So this is brittle. It might be a quartz grain, right? Which has undergone more compaction. The next type of compaction you have is chemical. This is chemical compaction, and it involves dissolution of the grain. Solubility of silicate minerals tends to increase with increasing pressure and temperature. Okay. So let's say you have quartz grains and they are in contact with each other, right? Now, first, because of sediment loading at the top, it undergoes mechanical compaction. The arrangement changes, right? The packing changes. Porosity is reduced. But after some time, you cannot really reduce any more space because the grains are brittle and rigid. Okay. So what happens is that you have high pressure contacts between grains, right? Maybe you have point contacts here. Now what happens is at the point contact there, the minerals start to dissolve. Okay, they go somewhere else. So your grains start to become sutured to each other in this case. So you get this zigzag pattern because of suturing. Okay, and that is dissolution of grains. Now become sutured together. They're stuck together now. Okay, so that is the first process in lithification. That is compaction. Then you have cementation, which is the process of deposition of dissolved mineral components in the pores of sediment. Like I said, most sediments are deposited in water. Fluids fill the pore spaces between the grains. The fluid contains dissolved minerals. As pore fluids flow through the buried sediment, dissolved minerals precipitate on the grain surfaces here. Given enough time, enough intergranular material is precipitated, and it glues the sediment together into a rigid cohesive mass. So you go from a sand to a sandstone, which is cemented by a mineral. So lots of different kinds of minerals can form a cement between grains of sand. Quartz is a common cement. Carbonate minerals like calcite are a common cement, and also aluminosilicate clays. Less common cements are minerals like anhydrite, pyrite, feldspar, zeolite, hematite, and sphene. So lots of different minerals can form a cement. So I have an example here under a thin section, which is under plain light. The white colored material are quartz grains. The moderately sub-round, these are sub-rounded to angular, right? The grains here. Sorting is it looks like it's moderate to poor. Now notice the dusty material in between, right? So this is calcite cement. These were not primary grains. They were precipitated here after deposition. They filled in the pores, so they have reduced porosity. Okay, so I have calcite cementation in this quartz sandstone. All right, so we've learned about textural properties. We've learned about porosity and permeability, and we've learned about lithification, right? Cementation and compaction. Let's see how all these related to each other, right? Porosity and permeability are two important properties because we have two economically important properties, right? They are very useful in the fields of hydrogeology and also in petroleum geology. Okay, so we need to the hydrogeologist or the petroleum geologist needs to know what kinds of factors affect porosity and permeability. What kinds of factors reduce porosity and permeability? What kinds of factors increase porosity and permeability? Okay, so let's go through that. Okay, look at the effect of texture and lithification on porosity and permeability. Both these properties, these are two important properties of sediments and sedimentary rocks in terms of their ability to store fluids, hydrocarbons, and water, for example. The magnitude of these two parameters for any particular rock depends on the composition of the rock, for one thing, and also the texture of the rock. And the composition and texture of the rock is determined by the history of deposition and barrier. Goes back to sedimentation, goes back to diagenesis. That is why sedimentology is important in hydrogeology and also petroleum geology. Okay, so we go one by one. Let's look at the textural controls on porosity. How does different textures affect porosity? Let's look at sorting is very important in determining the porosity of a reservoir. Okay. In sandstone, porosity is largely controlled by sorting. So I have two sands here. Okay, let's make it sandstone. Sorry, yeah? The sedimentary rock easier. For me, easier. So you have one sandstone here which is well sorted with okay. It is filled in with a fluid colored blue here, where black material are the grains. Okay, so this is porosity, right? And below is another sandstone with which is poorly sorted. Now you have these finer particles in between the larger grains, and it's infilling the pore throats. Okay, so if a sand is well sorted, grains about the same size, you don't have any finer size grains to fill in the pore spaces, right? So you tend to have a higher porosity. You have larger holes. But if it is poorly sorted, there's a lot of finer grain material inside your pores here. Now the volume of pore is now much lower because you have these solid grains inside the pores here, right? So the general rule is this: porosity generally increases with sorting. Better sorting, higher porosity. Poorer sorting, lower porosity. Okay, so sorting is important in controlling porosity. But what about grain size? Does grain size affect porosity? Generally, no. Why? So let's say in this case, let's say we have a sandstone here, and it is coarse grain sand. The grains are made up of spheres which are coarse grain, right? Now, if you reduce the size of the grains, the ratio between the grains and the pores is still the same. So there is no change in porosity. The volume is still the same. Okay? You're just breaking down the grains into smaller particles, into smaller grains. So yeah, the percentage, the fraction of void to total rock volume does not change with size. Okay, so no effect on porosity due to changes in grain size generally. Okay, so sorting affects porosity, but not grain size. Let's look at permeability. In terms of permeability, both grain size and sorting are important. Grain size, permeability generally increases with grain size. Okay, so two examples here. One, I have a coarse grain sand. The next one, I have a fine grain sand. Right? These are your grains. The blue is your pores, right? So notice when you have larger grains, you have, well, and you have fewer contacts between the grains. Okay, but when you have smaller grains here, there are lots more contacts between grains. Okay, so if you have a pathway for fluids to flow here, it's going to be less tortuous, we say, easier to flow, right? But here your pore spaces are smaller, and it's going to get harder to get from one point to another, right? Get a more tortuous pathway. So there are fewer grain contacts in coarser grain sand compared to finer sand. Coarser sands tend to have a higher permeability. Finer sands have a lower permeability. Right? Sorting is also important. Permeability generally increases with sorting. Right? So in a well-sorted sand, you have nice, large, interconnected pores. Right? And the flow pathway is more straightforward because go through here and move next to here. But in a poorly sorted sand, it's going to look like this. The pathway is now more tortuous. There are smaller pathways here. It becomes more and more difficult for the fluid to move from one point to another, right? Because the pores are clogged by finer grains inside poorly sorted sand. Okay, so remember that porosity, porosity, sorting is important. Permeability, grain size, and sorting is important. Now let's look at the effect of burial and lithification on porosity. Now we talked about this already. Mechanical compaction affects porosity. Compaction during burial can result in rearranging of the grains. So you get different packing, right, to the grains, right? So depending on the way of the grains are packed, you get different porosities. Yeah, so if you have ideal perfect spheres arranged on top of each other like this, porosity will be 48%. But if you pack it in another way, let's say for a rhombohedral packing arrangement, it will be reduced to 26%. So packing is important, and changes to packing is caused by mechanical compaction. And remember, compaction can also result in brittle and ductile deformation, which can also result in losing porosity. Okay. Chemical compaction results in dissolution around grain boundaries. Right? There was empty space in between before, but now they're much closer. They're now sutured. There's no empty space in the middle, so you are reducing porosity. Okay. Of course, cementation will reduce porosity. For example, right here, you have the original grains here with original porosity in between. When you start to get cement, so there is no porosity now. Right? Everything has been filled in this case with calcite cement. Right? But just be careful, this is not always the case. In some minerals, can actually grow larger. So the process of dolomitization, precipitation of dolomite in between grains, can result in larger pores. They push the grains further outwards because the crystals are growing larger and larger. So this is a generalization. Generally, cementation reduces porosity. Now, dissolution affects porosity the other way around. Right? So let's say you have a cemented sandstone here, quartz grains with calcite cement. Now, maybe acidic rainwater is percolating through the pores. Your calcium carbonate is dissolved. You start to get new porosity, and this is secondary porosity, right? This is newer porosity, and yeah, now you are increasing porosity. You're going the other way around. Okay, so that is how burial and lithification controls porosity. Let's look at how these two processes affect permeability. Now, fracturing and dissolution may increase permeability. For in the case of fracturing, let's say you have these you have a mudstone with pores, right? But the pores are not connected. But then maybe because of faulting, you start to have fracturing, and the fractures can actually form the conduit connecting once isolated pores. Okay, so fracturing may increase permeability. Dissolution may also increase permeability. For example, you start with a cemented sandstone here, right? So you have grains of sand, you have pores, but you also have some cement in between. So in this case, fluid cannot flow from one point to another because you have a cement in between. It's impermeable, right? So fluid flow pathways, we say, could be tortuous or may not exist at all. Now, because of dissolution, your cement is destroyed, and now you have a good pathway for fluid flow. So in this case, you are increasing permeability. Now, if it is the other way around, like in the case of porosity, so first you start with open pores, but then you start to get cementation, well, you are decreasing permeability now. Okay, so that is how barrier lithification controls permeability. Okay, so that's it for part 2. Yeah. See you in the next class.